In this learning objective, we're going to be looking at the difference between a standard delta G and a non-standard delta G. Students often don't see the nuances and the differences between these two, so I'm going to try to help you work through thinking about the difference between them. We know that this equation, delta G equals delta H minus T delta S, would apply whether you're in standard state conditions or not in standard state conditions. What is the difference between the standard state and non-standard state? Well, let's review what it means to be in standard state conditions. That means that the pressure is at 1 atmosphere, and if it is a solution, then it would be 1 molar. And when you look in tables for standard values at thermodynamics, they're usually at 25 degrees Celsius, though they don't have to be considered standard state. Now, if we started out every reactant and product in a reaction in these standard state conditions, let's say they're all gases, and every gas was at 1 atmosphere in there, not just your reactants, but your reactants and your products. This system is very unlikely to be at equilibrium under those conditions. So if it's not at equilibrium, then it's going to proceed either to the right or it's going to proceed to the left. Now remember, if delta G standard is negative, we know it's going to go to the right to get to equilibrium. It is spontaneous in the forward direction. If standard delta G is positive, it's going to proceed to the left in order to get to equilibrium. The reverse reaction is spontaneous. Now, if you wanted to know a standard delta G at a temperature other than 25 degrees Celsius, then this is the equation that we would use. You would look up in tables the delta H standard and the delta S standard, and from that information, these values don't change very much with temperature. Delta G is very affected by temperature. So if you put those standard delta H and standard delta S, even though they're at 25 degrees Celsius, and you put in your temperature, and don't forget to use kelvins when you do so, then this is going to give you the standard delta G at a temperature other than 25 degrees Celsius. If you needed delta G at 25 degrees Celsius, and it's standard, then you might as well just go to the tables and determine the standard delta G for the reaction and not use this equation. So we have a series of questions that I want you to think through in order to figure out the connections between what is delta G standard telling you and how does it change when you leave standard state conditions. So I have a reaction, and in this reaction chamber I'm starting with every gas at 1 atmosphere. So that's what's being represented in that picture. That is a standard state condition. We see here that the standard delta G is a negative value, a negative 190.5. So if I started everything out at 1 atmosphere, which statement would be true? Would the reaction shift to the right to get to equilibrium, shift to the left to get to equilibrium, or neither? It is already at equilibrium. If you said A, you'd be correct. A negative value for standard delta G says, and this is all it says, it's a snapshot. It says if we started everything out at 1 atmosphere, this reaction would proceed to the right because it's negative. Okay, let's again start this system out at equilibrium. Start the system out with everything under standard state conditions with 1 atmosphere. So we're here. We know according to this standard delta G that if we start everything under standard state conditions, the reaction would proceed to the right. Now, if it's going to proceed to the right, what is going to happen to the pressure of HCl? Well, if you said it would increase, you would be correct. The HCl pressure is going to go up, and these pressures are going to go down as it proceeds to the right. So it's always going in forward direction. The reverse reaction are always happening, but more of the forward is happening than the reverse when you have a negative 190.5 kilojoules, when you have a negative value for that standard delta G. Now, as soon as it starts proceeding to the right, my question for you is it still under standard state conditions? Well, no, because if the pressure is going up, it is no longer 1 atmosphere, it is greater than 1 atmosphere. And if it's greater than 1 atmosphere, then we're not under standard state conditions, and this number of negative 190.5 no longer applies. It only applies when we're in standard state conditions. Okay? Just to think about this, doesn't really give us a good connection between standard and non-standard delta G, but what's going to happen to the total pressure of this system as you establish equilibrium from the point at the beginning where everything is 1. It starts proceeding to the right, and it finally gets to equilibrium, and the forward and reverse reaction are happening at the same rate. What is going to happen to the total pressure? If you said stay the same, then you're correct. The pressure of HCl is going up as it proceeds to the right. The pressure of H2 is going down. The pressure of Cl2 is going down. Because the number of moles on the left, which we have 2 moles of gas, now it's not just moles, it's moles of gas. And there's 2 moles of gas on the left, and there's 2 moles of gas on the right. Then, as this reaction shifts, the total pressure is not changing. Okay, now here is a question I really want you to think about. When the equilibrium is finally established, okay, so what's happening here? We started everything at 1 atmosphere. We saw that at 1 atmosphere we know that the standard delta G is negative. That tells me this reaction is going to proceed to the right to establish equilibrium, and it finally gets there. Once it establishes equilibrium, what's going to be the value of the standard delta G? Will it increase to get to equilibrium? Will it have decreased when it gets to equilibrium? Or will it stay the same? Students often miss this, so don't feel bad if you didn't, but you've got to get to the understanding of why it would stay the same. A standard delta G is a snapshot of where it would be if everything were at 1 atmosphere. So standard delta G never changes. Its value is a negative 190.5 kilojoules per mole for this reaction. As soon as the reaction leaves these 1 atmosphere conditions, we no longer have a standard state condition. But the standard delta G is the snapshot of what it is when everything is that. So don't think that your standard delta G is going to change. But your delta G without the circle, it certainly will change. So our next question is to think about what is happening to delta G once you establish equilibrium. Will it be positive? Will it be negative? Will it be equal to 0? If you said it would be equal to 0, you're correct, and that's exactly what happens. Delta G equals 0 at equilibrium, not standard delta G. The only way standard delta G could equal 0 is if when everything was at 1 atmosphere, this thing happened to be at equilibrium. Very, very unlikely. Very unlikely. Well, this reaction certainly isn't. It had a negative value. We know it'll proceed to the right. We will build up more and more of these two. We'll use up some of this and some of this, and finally it'll get to equilibrium. And when it gets to equilibrium, at that point, the delta G for the reaction, it's no longer in standard state conditions, is 0. And that is true for every reaction. It's delta G is equal to 0 at equilibrium. So what happened to the delta G? The delta G started out when we were all at 1 atmosphere with this number. It gets to equilibrium, delta G non-standard is equal to 0. So the negative delta G is increasing as the reaction keeps working its way closer and closer to equilibrium. Now we're going to look at the mathematical relationship between the standard and the non-standard delta G. There is a connection. So anytime you need a non-standard delta G, it's when you're not in standard state conditions. And we have this equation to help us get to a non-standard. So if we wanted to know whether a reaction was going to proceed to the right or proceed to the left, and we had conditions other than standard state conditions, then this is the equation that we would use. The R that we use in this equation is the 8.314 because it has the energy unit of joule, and you would actually probably have to convert it to kilojoules before you could add those terms together. We see that a Kelvin is here in this K, and that's what we have to use for the temperature. And our Q is the reaction quotient. And the reaction quotient, if we remember, for a reaction is just like a K, equilibrium constant. Its products and its concentrations if they're aqueous, its pressures if it's gases, but its products over reactants raised to the power of their coefficients. Okay, so there's some coefficients of the balanced equation, it's raised to those powers. So that's what the reaction quotient is. So we can look at this reaction and say, okay, at this point in time, there is this much product, there's this much reactant. Let's put those numbers in there, and let's obtain a value for a non-standard delta G. Now, if everything were 1, then Q would be 1, okay? And if Q is 1, the natural log of Q is 0, and this term goes away. And that makes sense. Okay, so we're just going to think through this equation in terms of how does changing Q affect the delta G. So let's start with a standard delta G that's negative. This means that the reaction is spontaneous in the forward direction. That's what if you were in standard state conditions. So we put everything in our reaction chamber, and this is kind of like our little questions that we went through. Our standard delta G was negative. The reaction is spontaneous in the forward direction. So the question is, what would we have to do in terms of conditions? What would we have to do in terms of Q here in order to make delta G positive? Well, if the delta G is positive, we know that it's no longer spontaneous in the forward direction. It is now spontaneous in the reverse direction. How do we make delta G positive? Well, the only way we can make delta G positive is to make this term positive. Well, this term is positive when Q is what? How do we make the natural log of Q a positive value? Well, if Q is greater than 1, it's a value that's bigger than 1, then the natural log of Q is positive. Okay, so that's the first thing. As long as Q is greater than 1, then when we take the natural log, it'll be positive, and this term that I have circled up there is going to be a positive term. We just got to make it positive enough. So any time that the products are greater than the reactants, because remember what Q is? It's products over reactants, remember? Raised to the power of their coefficients. So anytime products is greater than reactants, then the Q is going to be bigger than 1. And the natural log of Q will be a positive value, and we can get it positive enough to overcome all the negative that we have here, and we can turn a reaction that was spontaneous in the forward direction to be spontaneous instead in the reverse direction. Well, let's go through that same mathematical logic in the reverse. Okay? What if the standard delta G was positive? So the reaction is not spontaneous in the forward direction. It is only spontaneous in the reverse direction if everything were under standard state conditions. So we start everything in standard state conditions. We know the reaction is going to proceed to the left. Okay, so that's what a positive means. It's spontaneous in the reverse direction. What conditions would we have to have in order to make this negative? We want this reaction to proceed in the forward direction instead of in the reverse direction. Well, let's think about what has to happen to this term. In order to make this reaction become spontaneous in the forward direction, this term is going to have to be very negative. It's going to have to be negative enough to overtake the positive of the standard delta G. Now, how can we make that term negative? Well, the only way we can affect that term, R can't change, it's always the same. Temperature is Kelvin, there's no such thing as a negative Kelvin. So the only way we can make this term negative is to make the natural log of Q negative. So if Q is less than 1, okay, it's a fraction, it's less than 1. Anytime you take the natural log of a number less than 1, it's negative. So how do we make Q less than 1? Well, once again, we remember that Q is products over reactants. Okay, raised to the power of their coefficients. As long as you have a lot of products, so this is a big number, and this is a small number, okay, so products is smaller than the reactants, then you're going to have a number less than 1, and as long as it's small enough, this natural log of Q would get negative enough that we would have more negative than we have positive, and that would make my non-standard delta G negative, and we can force this reaction to become spontaneous in the forward direction. Now, you're going to be doing mathematical numbers for this. It's not a big deal. You just got to watch your signs. If you're given a standard delta G and they want to know a non-standard delta G, this is the equation you will pull out. Watch your units. If delta G, which is typically in kilojoules, is given to you, and then we're going to have to make sure that this term gets converted to kilojoules before we convert it. The other thing you have to watch is your T and make sure it is in Kelvin, and you'll be able to easily convert between a standard delta G and a non-standard delta G. So this is the end of our learning objective number 9, in which we're seeing the connection between a standard delta G and a non-standard delta G. We see that they're not the same thing. We have to understand their differences, and we have an equation that'll help us convert between them.